Okay, so before we get started, just some announcements and reminders. So first of all, homework 9 will be due today, and based on how far we can cover today, so I'm going to post homework 10 maybe tonight or tomorrow morning, and it's going to be due next Wednesday. And over the weekend, I'm going to post like an announcement about all the detail of the presentation. So basically, the idea is, so first of all, you can see that I write down here that the presentation days will be mainly the week before the Thanksgiving, which essentially would be November 16 and 18th. That's essentially the week before the Thanksgiving break. So I hope everyone knows that because COVID, we actually kind of adjust the schedule. So now we are going to have one whole week for Thanksgiving break. So it will be the week before that. But since we have, depends on how many groups we are going to have, I expect that we probably will have a little bit more groups than usual. So basically, I probably would need roughly 2.5 lecture days to finish the presentation. So, but then I don't want to make it too early because I want people to have time to prepare. So basically, the main day would be the majority of the groups will be on 16 and 18th. And I expect there will be maybe two groups, around two to three groups that's going to be on the 30s. But it's kind of random. I wouldn't know right now that which group will be on the 30s. But essentially, I will use the first half of the lecture on the November 30th for the presentation. But the idea is that first of all, for presentation, there are going to be three components. First, it will be the oral presentation, right? Like whatever that you present on using slides or whatever through the Zoom. And the second component would be the written part. So depends on whether you're a group of one person or group of two, that there will be a written part because I still want to see that what's the written solution of the problem that you present. So I would need to ask everyone to turn in the hard copy of your written solution. So but each person need to turn in individually. So let's say if you work with someone else, let's say you're in the group of two people, then each of you should still submit the individual paperwork, that the hard copy, right? And I will explain more in the announcement, but just to tell you roughly what's the scheme here. So you will have the written solution. That's another component. And the third component would be the attendance. So attendance means that not only you're going to present at the Zoom lecture throughout the whole thing, and I'm going to ask you to take a note. So for example, when other people is presenting, you should take notes, just roughly write down what that person is presenting, right? What's the problem is, right? So I'm not going to be too harsh on the attendance part, but I'm going to ask you to turn back to submit your notes back to me. So I know you really pay attention to what people said, not just turn on the computer and leave and do other things, right? So you need to respect whoever is presenting, right? So that will be three components essentially for the presentation. And the goal of my presentation is to hope that most of you are going to be high school teacher, and then if you already taught before, then you definitely knew that it's actually not easy at all to explain math to other people, especially to other people who are not at your level, right? For example, if you're teaching really like students in high school who didn't have the same knowledge as you, then how to explain things that people don't know is quite difficult. At the same time that you need to do the presentation, you need to think at the same time that how to explain things, right? Or maybe also like during the presentation, I'm going to ask you the questions as well. And I'm going to let other people ask whoever presenting, also other people can ask the question to the presenter. So that would be the three components here. But you might think that, oh, it's a little bit unfair that because there will be some people going to present later. So don't think that whoever present on the 30 is definitely the one who take the advantage. Because first of all, I'm going to ask everyone to turn in the written solution on the 18th by 18th, even though you're presenting later. Okay. Second, for the week before during the week of the presentation, so the week before the presentation week, I'm not going to assign the homework, so then you can focus on the presentation. But there will be a much longer homework, which is the last one. It's going to be due on the last class day, I think is December 2nd. Because if you think about it, I'm not going to assign the homework the week before Thanksgiving break, the week before presentation. And then we have the presentation week plus the Thanksgiving week. So that essentially is almost 3 weeks without the homework. So the final homework is going to be much longer than usual. So which means if you don't prepare your presentation earlier, then you actually drag all the things till the end. So not only you need to prepare your presentation, then you also need to do the last homework, right? So definitely, I wouldn't say that whoever present on the third day is going to have advantage. It's not. It depends on how you view it, right? I don't think it's an advantage. Okay, so I'm going to. So the way I did it is the following. So I'm going to post announcement, and what I did is I will pick out some exercise. Every problem pretty much is, or the project that I want people to do is pretty much from the textbook exercise. As you can see, some of the exercises are longer and have more questions. So I'm going to pick several exercises from different sections throughout the whole things that we have learned before. And then I will specify that this problem is for one person, or this problem is for group of 2, okay? And since we don't have that much time, so unfortunately I cannot get everyone to do individual group, which means that there's some of you, or actually majority of you, will have to find a group member, a partner to work with, okay? And then so I will specify which problem is for one person, which one is for 2 people. Then it's on the first come first serve basis. So basically, I will give you some kind of Google document, so you can fill it out that whoever, person A and person B want this problem 1, and the other person want problem 2, and it's first come first serve, right? And then once you decided, once everyone filled out the document, then I will decide whoever present first, what's the time schedule here. So once I open up or make the announcement, then you can go ahead and then pick the problem you like. Okay. So yeah, so you can read a little bit more of the announcements. I'm going to show the announcement to you over the weekend, so you can start preparing as early as possible. Okay. And if you have any questions regarding the rules, you can ask me, and probably I will explain a little bit more on Monday after you read the announcement. Okay. Okay, so before we go back to 15.1, what I want to do is the homework problem that I just graded. So I'm almost done with this homework A, so I'm going to return it by tonight. But I've seen a serious issue on this second problem. So first of all, I want to warn everyone that from what I saw, especially this problem, I have this feeling that people start getting a little bit sloppy, in the sense that I've seen people write very short and just give me a bunch of equations without clear evidence, or even didn't give me a complete sentence. Okay, so that's not okay. Okay, that's not acceptable. This is homework. This is not exam, right? You have plenty of time to write a proper answer, right? So please use the complete sentence. Do not give me a whole bunch of equation without explaining it. It's very hard to tell which one is your evidence, which one is your conclusion. Okay. And second, I start seeing people either, I don't know whether you guys copy each other or maybe because you discuss. So I've seen very similar answers, or actually I should say similar mistakes. Okay, that's actually how I find out that people copy each other in this, or maybe mimic each other, in the sense that there are several people making exactly the same mistake and then putting exactly the same thing. Okay, so I'm not saying that you cannot discuss the homework with others, but first of all, let's say person B asks person A for advice or hint. Then person B should actually make sure that he or she make sure whether he or she understand the whole thing and write his own answer. Okay. And then by saying like understand, it means that you really need to question every single step, right? Like when two people are discussing homework, you should not just take other people's answer for granted, because what if that person actually give you the wrong answer? How did you know, right? So for doing mathematics, you should always question other people's answer, right? Even me, for example, that when I present to you something, you should always ask yourself, or actually trying to convince yourself that this is correct, because I may make mistakes sometimes. I may overlook something, right? So by actually asking other people questions, you're actually helping that person, because maybe the answer or the advice that person give to you is wrong, right? Then by making sure that you ask the question from each step, how to go from step 1 to step 2, you're also double checking the answer for that person. So please, if you want to discuss the homework together, make sure that you, both of you or three of you, actually get the correct answer, right? You should not just directly copy from one person and take it as it is, right? It might be wrong. Actually, I saw several wrong homework answer like this. So that's one thing. So first, I'm going to tell you what's the correct way to prove it. It's not the only way, but from my opinion, it's actually the fastest way and most straightforward. I've seen other way of proving it, but it might be a little bit detour or something. Sometimes you might have redundant steps. So for example, this problem tells you that you have a parallelogram. So I'm going to tell you the correct way of doing it. Then I will point it out the common mistake I saw, that people give me a certain proof which is not correct and has some gap. Okay, so first of all, you have a parallelogram ABCD, and you have E and F as the midpoint. And the question is, you want to prove that the diagonal is being trisected, which means you're going to prove DG equals GH equals HB. Okay, so first of all, because it's parallelogram, right? So I'm going to be sloppy because I don't have time to write down the complete sentence, but I'm just going to tell you what's the condition we have here. So because it's parallelogram, then by essentially proposition 1.34, we right away has the fact that AB equals CD. And I mean, actually, this is all we need. So AB equals CD, right? But at the same time, because ABCD is parallelogram, so we know that AB is parallel to CD. That's essentially the definition for parallelogram. Okay, so now if this is the case, then since E and F are midpoints, so we know AE equals EB. But at the same time, we all know that it's going to be the same as CF and FD, right? Because essentially the AB is the same as CF, and then they cut it half, right? So we have all these four smaller segments are equal. So now what we have is AE equals FC, right? And also, because AE is part of the AB, so AE is going to be parallel to FC. Okay, so now the first thing, like what I mentioned in the hint of this homework problem, is that first thing you want to prove that AF is going to be parallel to EC. So I've seen a reverse logic in the homework. This is also a common mistake. So your argument should be like this: because AE equals FC and then AE parallel to FC. So by proposition 1.33, that tells you, this implies you have the opposite side will be parallel. And they're also equal, AF equal. And by proposition 1.33, because then you can get AF equals EC. So I've seen several people trying to do a lot of either wrong argument or detour trying to prove this fact. This is simply just because AE equals FC, right? You have AE equals FC, and then they are parallel. So by this proposition that we saw before, then the other pair will also be equal and parallel. And then because now you have a second pair of parallel sides, then this is implicitly tell you that essentially you have a parallelogram AECF. So what I've seen, the common mistake is that people tell me first, you get a parallelogram, so AF equals EC. That's wrong, right? The logic is reversed. you actually first know that AF equals EC because the proposition 1.33. So you know that it's a parallelogram, not the other way around, okay? Because the definition of parallelogram, let me emphasize again, I still see people do it wrongly. The definition for parallelogram is you have two pair of parallel sides, right? So two opposite pairs should be parallel, and that's it. Nothing to do with the length, right? The definition of parallelogram is it's pretty much in the name, right? It's two pair of the parallel sides. Okay, so that's first thing. Once you can prove this is parallel, then we are in a good shape because now these two AFEC are parallel. So we are going to look at two different triangle here. One is A, B, and G, right? And the other would be D, C, and H. Okay, so let me copy down the picture here. So now I have A, B, and G. And you have E, H is parallel. Okay, so now we know that EH is parallel to AG. And that's where you can use the proposition 6.2. So by 6.2, what does this tells you? This tells you that then you have a ratio here to compare. So the ratio tells you that, okay, if these two lines are parallel, then BE over EA would be the same as BH over HG. Right? But now what do we know about BE over EA? They're equal, right? So this is actually 1. The ratio is 1. So if ratio is 1, then this tells you that essentially BH equals GH. Okay, so now you know BH equals GH. So I think people just, without writing this ratio, just kind of roughly explain what happened to me. This is not enough, right? It's a bit vague. So you should actually tell me, if you're quoting this proposition, you should tell me, show me the ratio, right? You need to show me the work, because sometimes I really don't know whether you're just guessing it or you really know how does it come from. So for the homework, I'm always being a little bit strict that I want to see the argument. So I'm sure that you really know what's going on, not just trying to hide some detail. Okay, so usually the more detail you hide, usually it reflects that you are not sure about like the detail. That's why you don't want to show it. Okay, so then first we can get BH equals GH. Okay, that's the first thing. Then you just simply do another like argument with the what's DCH, right? So you do it again with DCH. So am I DCH? Yeah, actually wrong shape. Sorry. D. What's the shape here? DCH. Okay. So I have DCH, and this should be FG. So you do the same argument, right? So since FG is parallel to CH, right? So again, by proposition 6.2, then you know we have the ratio GF over FC is equal to DG over GH, right? And same thing, because you know this ratio GF, you know, actually, sorry, DF, right? So DF is equal to FC. So you know the ratio is actually 1. So if it's 1, then it tells you DG equals GH. So now combining these two things you prove, you can really say that those three segments are all equal. So it's really simply using 6.2 twice, pretty much. And before you can use 6.2, you should use like some of the information to get the fact that AF is parallel to EC. And that's really all you need here. Okay, so please, especially this problem, I've seen a lot of issues. So you should definitely go back later on when I returned it tonight. You should go back to like check your solution. So the common mistake in this part, what I saw is actually the where I saw a lot of like sloppy answer or gap. So a lot of people actually just show me. Let me copy the picture. Oops, sorry. Picture again. So this is DCBA, EF, and this GH. What I've seen is that some people trying to tell me, so first of all, I've seen a lot, so some people trying to prove this is the wrong answer, okay? So some people trying to tell me that the triangle DCH is similar to triangle BAG, okay? But whatever argument you use, okay? So first of all, what I've seen some of the mistake is that people trying to tell me it's similar, but for whatever reason, in the end, they show me congruent. Or actually, some people claim it's congruent without giving me a proper evidence. Or actually, some people give me two angles are equal and then directly tell me it's congruent. Okay, it's not, right? AA or AAA, it's not a congruent scheme. It's similar, right? So so if you want to prove similar, then you need to tell me it's similar, whatever similar scheme, right? You cannot claim congruent triangle by giving me a similarity evidence. Okay, that's also some mistake I've saw here. And then even you tell me, okay, it's similar, then the first thing people will show me is that then the sides BA over DC is equal to, I don't know, like BA over DC, it's CH over AG, and also says something like DH over BG, right? Okay, that's correct. That's the ratio you will get if two triangles are similar. And then right away, the gap is then people directly jump to the conclusion that those three sides are equal. I really want to ask that, do you really think it's equal? Because from here to here, it's actually a very big gap, right? Where's the middle argument? Do you really know it, or you just actually copy from other people's answer and then you think it is, and then you just be done with it, right? I mean, there's a big gap, right? Why this three will suddenly become true? I mean, DH and BG is here, right? But it's none of none of the segment below, right? So there's actually a huge gap, right? And second, actually, you didn't really get the conclusion you want, right? So even you tell me, okay, even you fill in the blank that, okay, because BA equals DC, right? So you say, okay, this ratio is 1. That's correct. Then what you get is actually DH equals BG. What you tell me is DH equals BG. Okay, then what you can prove at most is by subtracting the common segment. Then what you actually prove is tell me that DG is actually the same as BH. Okay, so you just tell me DG is the same as BH. That's the best result you can get. You don't know anything, nothing, not information, nothing about GH, right? So the only thing you can claim from this kind of proof is that DG is equals to BH, but you have nothing, or you don't know nothing about GH. So actually this proof does not work. So I've seen so many of people give me this same answer and just directly jump to the gap, which I don't know how do you get it. Second, I don't know, like maybe you haven't thought it through, or you just maybe directly believe what other people tells you, right? So this proof would not work. Okay, you need to use somehow the ratio like this, like 6.2, to get the correct ratio. If you use this one, then you will only prove half of it. Okay, so I believe whoever did this, I gave probably 3.5 out of 5 points, and then if you have more mistake, then it will be below 3.5. Okay, so I know a lot of people did this. Okay, because I remember who actually did this. So it's actually quite a lot of people give me similar argument like this. Okay, so I don't know, maybe you thought of it wrongly, or actually because you copy other people, or maybe you just simply naively believe what other people say. That's why I said I'm fine with you guys discuss the homework, but I'm not fine that you take it as it is without understanding it, or without like really convincing yourself. Okay, you're not going to learn anything just by copy other people's homework, right? Not just this class, in other class as well, that I have a lot of students who did perfect, almost perfect on the homework, but in the exam, they do very poorly. And the reason we all know very clear is because probably they didn't do the homework themselves, right? They have some help, they maybe copy from some solution manual or maybe from other people so they can manage to get the homework done. But since they didn't really come up with the answer by themselves, so that material doesn't stick with them, right? Because you're just watching people do it. So you didn't really learn it by heart. So when it comes to the exam, when I change the problem, then suddenly you don't know how to do it, right? So I don't want to see this happen, okay? So please make sure you know how to do the problem really by heart. And then if you don't know how to do it or have questions, please come to ask me. Okay, so that's essential. So is there any question for the homework for this problem? So I'm going to post the solution so you can see it. Like, I mean, of course, there might be some other way to prove this problem, but I believe this is actually the most straightforward one without having to prove two triangle is similar or congruent. You don't have to. Okay. Okay, so so I'm going to go back to 15.1. Okay, so what I'm going to do today is I'm going to pretty much finish the proof here, and hopefully we can start the 15 point. I'm going to finish 15.1, and hopefully we can start 15.2. So let's continue to talk about isometry. So I want to recall the definition here. So this is the definition from Monday. So what's an isometry? Isometry, or sometimes people call it rigid motion, is a transformation. Transformation means it's a mapping from R2 to R2, from a plane to a plane, okay? And so remember last time we talked about an isometry need to be a surjective, an onto map, onto R2, okay? But the key point is actually isometry is something that's preserving the distance, okay? So that means if you give me any points from the domain from R2, then the distance between A and B should be the same as distance between f of A and f of B. So in other words, f preserves the distance. This isometry preserves the distance. Okay. So before we really prove some nice property about isometry, I want to show you that just by using this definition, I know that isometry is actually injective, right? So in calculus, you know that there's always like either injective or surjective, right? Those are two different property, right? And then if you have both injective and surjective, or you can say both 1, and onto, then this map will be bijection, right? So actually just from the definition that isometry is onto a surjective map plus preserving the distance, then you can actually show that it's actually automatically an injective map. It's a one-to-one map. So I want to show you because it's just pretty much one line proof. Okay, so what do we want to prove here? Let's recall the definition for injective. So injective means that if your output is the same, if f of A equals f of B, then your input should be the same, right? This is actually the definition of injective, right? So now we only need to prove if you start with f of A equals f of B, then you want to prove then this has to be the case when A equals B. Okay. So now let's start with f A equals f B, right? Then if you have 2 points, f of A, f of B, which are exactly the same point, then on the plane, we know that because they're the same point, then the distance should be 0, right? You're talking about the same output, right? So the distance between those 2 points are 0 because they are the same point. Okay, but now it's the time we use the definition of isometry because it preserves the distance. So we know that the distance between f of A and f of B should be the same as distance of A and B, right? This is because by the definition of isometry. Or you can say it because, in the definition, it preserves the distance, right? So then we know that on one side, the distance between f of a and b equals 0, right? So we know that it tells me that a and b, the distance should be 0. Okay. And we know the only situation where you have 2 points, the distance between 2 points is 0, is when those two are the same points. That's essentially the kind of the property we use from having a distance, right? So you can see that that's actually pretty much one line, right? And it's really exactly because isometry preserves the distance. So right away, if it's isometry, you know it has to be injective as well. Okay, so we don't necessarily need to include it in the definition because it's automatically true. Okay, so now we have actually very good property, right? So by the definition of isometry, I know it's onto. Now I can prove by the definition of isometry, it's also injective. So it actually tells me isometry is a bijection. So isometry is a surjective and injective at the same time, meaning it's bijection, okay? So bijection means that inverse map exists, right? This is something you saw it in calculus, right? So that's why, I mean, you need to take few calculus class before taking this class. So we know that inverse map exists, right? So if it's so what's inverse map means, right? Which means if you have any isometry f, then you will have inverse map, right? Inverse map, the definition is if you compose the inverse, whatever you call it, let me call it another map G, then the inverse composed with F should be identity map. And also F composed inverse should also be identity. But be careful, having a bijection only tells you that the inverse map exists, but it doesn't tell me whether the inverse map is an isometry as well, right? It's definitely inverse is going to be onto as well, but how do I know whether the inverse map preserves the distance? I don't know yet until I prove it. So one of the exercise is I'm going to assign maybe this homework or maybe next homework. You need to show that the inverse map of an isometry is also an isometry. So essentially, you need to prove that the inverse map also preserve distance. That's the part that you need to prove, preserve distance. That's not so obvious, right, from what we know. And on top of that, this is actually, maybe I shouldn't separate into exercise 1 and 2 because exercise 1 is part of the thing you need to prove for this second exercise. So it turns out that you can show if you collect all the possible isometry from the plane, it's going to form a group. And the operation here is by using the composition, right? So let's recall what the group means, right? To form a group, there's a 4 criteria, right? First, you want after the operation, the new element is going to lies in within the O1. So if you have A compose G, you want F compose G also lies in the set of isometry. Meaning, if you have 2 isometry, F compose G should also be isometry as well. That's the first criteria you need to check. Second, you need to show that identity map exists, right? So identity map exists in this, identity element exists in this set. Third, you need to show that the inverse also exists in this set. And the inverse part is exactly this first exercise, right? You need to show that inverse exists and it exists in this set, meaning that the inverse is also isometry. That's why I say part 1 is probably kind of included in part 2. And the last part is to show that your operation is associative, which you can automatically assume to be true because a composition action is always associative. Meaning, if you compose a function, if you compose function like this, then it's going to be the same as composed in this different way, right? So the composition is usually always associative. So there are 4 things you need to check here. And I'm going to leave an exercise. This is quite difficult. I can tell you that from my experience last year that not many people actually can do this exercise correct. And then so I want you to think about it. And then if you have any question, you should come to ask me. Please do not just randomly copy some answer from somewhere. Okay, so last year what happened is that I've seen 6 or 7 people give me exactly the same wrong answer. Okay, and if I've seen that, I'm going to tell you right now that I'm going to take points off. Okay, I don't want people just blindly copy some answer. Okay, so this is something that you need to think about it. But what we can say for now is that we can show this collection of all the isometry is going to form a group. And by assuming this, then we actually need to prove that the inverse map is also isometry. Okay, this is not obvious, you need to prove it. Okay, so now what I want to prove for the remaining for the 15.1 is that actually isometry has a lot of nice feature, because you can think of, in some sense, isometry preserve the distance, right? So if you plug in any 2 points from the plane, it's going to keep the distance, right? So whatever the output is, if even it's different points, it's going to keep you the distance, right? So think about what kind of action or what kind of map can be isometry. So think about mirror image, right? If you do a reflection, right, you have some kind of mirror image. Like if you look at the mirror, right, your distance from you to the mirror, it will be the same from the distance from mirror to your mirror image, right? Or let's say if you have 2 people standing in front of the mirror, and then the distance between you and your friend will be the same as the distance in the image that you saw in the mirror image, right? So reflection is definitely preserving the distance. So in some sense, if it preserves the distance, you can see that it will preserve a lot of shape, right? So first thing, we're going to see that if you have a line, then isometry is going to transform or map a line to another line, right? Because everything is kind of lined up, right? And then you keep the distance. But even more, you can actually show later on that isometry also keep the shape of a circle, right? Or actually a triangle or even an angle, right? It will preserve all the shape, everything, right? Because it keep the distance, okay? So first thing, this proof is actually not that easy. So I want to go over it because, I mean, if you just read it by yourself, it can be a little bit hard. So first thing, it tells me that in neutral geometry, meaning all we prove here does not depend on the fifth postulate. Oh, okay, only first 4 is enough. So every isometry is going to transform a straight line onto a straight line. So why I highlight the onto, it's because not only you map the line, straight line to a straight line, you also want to make sure that your image will be hit by all the inputs. So which means that, like for example, if you have a line, right, and you say, okay, I have an isometry here, right? You map this line to the target, right? Okay, but how do you know how do you know that all the points here is going to be occupy the whole line, right? It might be the case that, okay, maybe all the point is going to map only partial of the line, right? Like a segment, right? So what we want to make sure is that the line here from the input, from the domain, really get mapped to the complete line, not just partial of it. Okay, that's what we meant onto. Onto means that you need to cover everything in the target, right? So that's what we want to make sure. You really map an infinite long line to another infinite long line. Okay, so in order to prove this, there are 2 things we want to make sure, right? One thing is that if you pick out something from the line here in the input, it really get mapped to anything on this line, right? That's the first thing. Second, we want to make sure that your image can cover the whole infinite long line. So there are 2 things. So first, let's say if f, let's call f to be the isometry. And then I have a line, which is line AB. Then I want to show that the image, if you plug in this line into f, the image is also a line, a straight line. Okay, so there are 2 things I want to show. First, this is very a bit abstract. So first, if C is another point on the line, right? And I want to show the image C prime lies on the unique line join these 2 points. So what does that mean? It means, okay, so let's say I have a line AB here. and I get map F to something, okay? So I pick out a point C, maybe from between AB or maybe outside AB, doesn't matter. I'm just saying, okay, if I have a C here. And of course, if you have, let's say if you have A and B, right? Then what's the target? The target maybe this point is F of B, right? That's called a B prime. And you have a target maybe here, F of A, that's A prime. So what you want to make sure is that, okay, between A, B, there's a point C, or maybe along the same line, there's some other point C here, doesn't matter. But what I want to make sure is that after you get mapped by F, your image C prime should lie on the line join A prime and B prime, right? Because that's how you make sure that everything on the line get mapped to everything on the line, right? Something on the line. So you want to make sure that C prime is somewhere here, right? Or here, right? So C prime is F of C should lies on this line as well. And this line is actually the line A prime, B prime. That's the first thing, because you're afraid that what if you have a point C and you get mapped to something outside the line, right? Then you're not mapping a line to line, then you're mapping maybe line to a triangle or something like that, right? So you don't want this to happen. But another second thing, which we're going to show later on, is that what I said, you want to make sure that you map a complete line to a complete line, not just some segment, right? So that means now, once we know that it will be something on the line, but we want to make sure it will cover every point on this line L prime, right? So if you call this L prime. So we want to make sure if D prime is a point here, either here or outside anything on the line, okay, then you should be able to find a pre-image. You should find a point, maybe D here on the line, such that this D can get mapped to D prime. Okay, that's what we want, right? You want to have a corresponding input as well, right? Otherwise, if this is not the case, then you're telling me maybe the whole line can only get mapped to a small segment. Then you may not cover everything on L prime. Okay, so there are two things we want to check here. Okay, so let's do it one by one. Let's first do the first one here. So first one, that's C, right? So how are we going to do this? So first of all, so there are two cases. We need to consider two cases. First case is that you pick this point C you pick the point C that lies in between A, B. And second case is C is still on the line, but it's outside AB. Okay, so the two cases, the proof will be similar. So for the time being, I'm only going to prove just one case. Okay, so that's C. So we consider, use different color. So consider a point C on line L, which lies in between A and B. Okay. So first you pick out a point, and this would tells you what? So C is between A and B. You have actually a very good property regarding the distance. So if C is between A and B, then this is equivalent saying that your distance between A and B can be separated into the sum of distance from A to C plus distance from C to B, right? It's kind of obvious, right? If C is between A and B, then the distance, the length of AB can break into length AC plus CB, right? So this is kind of obvious, but it actually tells you that this is the key feature to show you that C really lies in between A and B, okay? So now let's keep this in mind, okay? So now we call C prime to be the image of C, okay? So let's say C prime equals F of C, okay? Now we want to see that what happened for the image, right? What's the distance in the image? So then what's distance between A prime and C prime, right? So A prime and C prime, what's A prime and C prime? A prime is f of A, right? C prime is f of C. That's how we code it. So you can see that later on in this section, a lot of time in the textbook or even in my proof, I'm going to call A prime, B prime to be like the image, right? Okay, so if it's f of A and f of C, then we know that because f is an isometry, right? So it's going to preserve the distance, right? So because, so let me add another one. So adding the distance between C prime and B prime, right? So this is f of C as well, and this is f of B, right? So this is going to be the same as f of, the distance between A and C plus distance between C and B, right? This is just by the definition of isometry. Because it preserves the distance, right? But we just know that distance between AC and CB added up is going to be the same as distance between A and B, right? This is something we just proved. And then what's next? Then, but now we do the isometry definition again, right? You're going to see that the reason I show you all this proof is that it's going to help you to see, to know how to use the isometry definition, right? Like one thing mathematicians do to learn a proof is by like reading a lot of proof so they know how to prove certain things. Okay, so now by the definition of isometry again, distance between A and B should be the same as distance of f of A and f of B. And that means this is the same as distance between A prime, B prime. So why I kind of go all this alone? So essentially it tells me you have a point C prime, which give you the fact or property that distance between A prime, C prime plus C prime, B prime equals A prime, B prime. Then what does that mean? Then it means it forces C prime to lies on the line between A prime and B prime, right? Otherwise, the distance will not add up to be the same, right? So this is exactly tells you that any points between A and B on the line, if and only if you see this kind of sum of the distance, right? So basically, this implies or means that C prime lies on the line A prime, B prime, right? Even more, it's actually between these 2 points, right? So really just by using, in some sense, by using definition of isometry, and then you just kind of separate it and then put it back together, you're using the definition of isometry twice, then you get the fact that this target point, this output C prime, should definitely also lies on the line between A prime and B prime. Otherwise, you would not see the distance like this, okay? So now you may question me, you should always ask me, okay, you only prove one case, right? Because you start by assuming C lies between A and B. But it's possible if you pick a point C outside A and B, right? But still lies on the same line. Then you swap the row of two of the points, right? Because you can see that if you pick A and B like this, and now if you pick a point C here, then you just swap the row of B and C in some sense, right? Now B is between A and C. So you can do the similar proof to prove this case. So I'm not going to do it because we only have limited time. So I will just make a remark here that the similar proof will hold. So similar argument holds when C is on line AB, but outside the segment AB. Okay. So after you prove the first part, it just tells you if you pick any points from the line L, then it should map to somewhere on the line L prime. Okay, somewhere. I don't know where, but somewhere. Okay. So, but now the second part, like what I said, is that now you want to make sure every point on line L prime should have a pre-image. Or in other words, once you map the line L to the target, you want the image to cover the whole complete line. You don't want to miss any points on the target, okay? So to prove this, then we start with a D prime here, which can be any point on this line L prime. And you want to say that this D prime is the image of some point D from the domain, okay? So that's what we want to prove. Okay, and the idea is very similar to using the distance. Keep playing around with the distance here. Okay, so now let's see. So we want f of d equals d prime. Okay, so first that d prime be any point on. So again, I also need to consider two cases, right? Because similar to the first part. So here I also want to do just the case when D prime is between A prime and B prime. And the similar proof will hold when D prime is outside A prime and B prime, as long as it's on the same line, okay? So let's say that D prime be any point on the line A prime, B prime. But in between these 2 points. Okay, that's first we start with the case 1. Okay, so then we know the same thing about the distance, right? So we know that because it lies on the line between those two, so you can see from the picture that the distance of A prime, D prime add up with D prime and B prime. This should be the distance between A prime and B prime, right? Just because they lies on the line between A prime and B prime. Okay, but we know A prime and B prime is essentially f of A and f of B, right? Actually, I should be careful. We don't know this yet. We don't know what's D prime, right? This is what we want to prove. We don't know yet, okay? So, so A prime, B prime is essentially the same as f of A and f of B. Now, by the definition of isometry, because they preserve the distance, so the distance between f of A and f of B should be the same as A and B. Okay, so that's the furthest we can get so far, right? So it tells me that, okay, let's call this distance D1 and distance between D prime and D2. So we know that D1 plus D2 will equals to the distance between A and B. Okay, that's something. Okay, so now let's see. So here I said, okay, there's a D1 here, whatever that is, and D2 here. Okay, if you look at my picture here, right, I said between A prime and D prime, let's call it D1, and the other one is D2. The only thing I know now is that, okay, then what do I know? I know that the whole distance of A and B is the same as D1 plus D2. That's the only thing I know, okay? So now the logic is the following. Now you say that, okay, I know that D1 and D2 should add up to the distance between A and B. And I want to break this distance into 2 segments. And you can imagine that between A and B, there should be only one unique point such that the distance from A is exactly D1 and distance from B is exactly D2, right? So if I give you, let's say if I give you like a rope, right? A segment of rope, which is 7 centimeters. And I say, please cut this thing into, cut one cut in the middle and such that it becomes 3 plus 4 centimeters. Then you know there's only one way to cut it. If you explicitly says, I want the distance from one end is 3, the other end is 4. I mean, there's only one way you can pick it, right? One way you can cut it. So essentially, this tells us that we know there is a unique point D on the line L, right? And between A and B. There's only one such point between A and B. And such that the distance between A and D is D1, right? And distance between B and D, or actually put D and B is better, D and B is D2, right? You can only pick one point. There's no other possible points, right? So then what does that mean? So what's D1? D1 is the distance between A prime and D prime. And the distance of D2 is D prime to B prime, right? So because I already know the total distance is fixed, right? So I say, okay, from point A, pick something that's D1 distance from A, and you pick something that's D2 distance from B, then you know it has to be, there's only one point you can choose, okay? And you call that point to be D, okay? So actually, I should probably said that before we don't know where D is, right? So I say, okay, we start from D prime. And I know between A prime and D prime, the distance is D1. Between D prime and B prime, distance D2. And now because isometry, I know the total distance of A and B is D1 plus D2. So I say, okay, pick out some point that's essentially give me the distance D1 here and distance D2 from to B. Then I say there's only one possible point. That's called it D. Okay, whatever that is. But the question is, I still don't know what's the relationship between this D and D prime. I didn't tell you f of D is D prime yet, right? That's what we want to figure out at the end. So, but now we really need to come back to the isometry. Okay, so but what's next? Then I know that essentially, let's check the distance here. But D and A, we already know it's D1, right? But D and A is the same as f of D and f of A, right? This is by isometry. Okay. But f of D and f of A, what's that, right? I don't know what f of D is. Oops, sorry. But I know f of A is A prime. Okay. And same thing, I know D and B by isometry is the same as f of D and f of B, which means this is f of D and B prime. Okay. So what do you tell me now? You tell me that the distance between f of D and A prime is the same as D1. And the distance between f of D and B prime is D2. What does that mean? So you tell me, so you don't know what f of D is, but you know the distance between f of D and A prime is D1, and to B prime is D2. Then you can see from the picture, there's nothing else. It has to be D prime, right? I mean, from the picture, we already start by knowing D prime has this distance, D1 and D2 to both of the endpoint. And now you tell me there's another point, f of D, lies on the line, have exactly the same distance to A and B, to A prime and B prime. Then essentially there's no other point but D prime. So what essentially from here, then this tells us that f of D has exactly the same distance, from A prime as D prime. And also f of D has the same distance from B prime as D prime, right? So it has to be D prime. There's nothing else. So basically, that's how we prove that D prime is really f of D for some point D. Okay, so this proof is actually quite hard. It really takes time. So I like, if you want to really understand the whole proof, I would say, please, you should definitely sit down and then read my proof, or actually read the textbook. My proof is pretty similar to the textbook proof, and you should try to understand the whole logic here. And I can say in the end, the similar argument holds if when D prime is outside A prime and B prime. So that's the second case. Okay. So basically, we actually prove what we want, right? So let me give you the conclusion here. I want to write one last conclusion. It's more complete this way. So what we prove, so hence, we proved that F maps every point of the line AB to a point on line A prime B prime, right? And at the same time, part 2 tells us that every point on line A prime B prime is the image of some point on the line AB. Okay, so that's second part is essentially proving the onto part. The first part is proving like your mapping line to another something on the line. Okay, so this is actually quite hard. I didn't expect everyone to understand right away. So you should take some time, think about it later on. Okay. So the next thing, since we already see this long proof, I'm not going to do this another long proof. So now we know if you give me a line, then isometry will transform this line to another line completely. Okay. Then we actually have this nice property that if in neutral geometry, if your isometry actually fix two of the points, any points in the plane, let's say A and B, then it's going to fix the line join them. What does that mean? It means if you have A and B, whatever it is, okay, and you map to exactly the same thing. So it tells you your image is the same. That means what? Oh, actually, it is B. In fix means that it fixed the points, right? So if you fix 2 points, that means f of B equals itself. It's B. F of A equals A, right? If you know this is the case, then this lemma 15.5 tells you, then you're going to fix anything lies on this line. So what does that mean? It means if you pick some point C on this line, then then the image of this C is going to be C itself. Or if you pick a D here, then f of D is going to be D itself. So it turns out that the image is going to be the original line. So it's essentially, this picture might be a bit misleading because when you fix it, it doesn't really move, right? But I want to show you this is the kind of the image. So essentially, it means if you're plugging anything along that line, then the image would be exactly the same thing as itself. So that's what it meant, that if you have an isometry which fixes 2 points, then it's going to fix anything on this line, on the line join these 2 points. So you can imagine that this 15.5 is going to use the theorem that we just proved. So the proof is going to use, so we need the theorem 15.4. So I'm just going to assign this as a reading assignment because I don't really have time to do all of them. So I'm going to just please read the proof as exercise. Okay, but the idea is if you give me 2 points and you know that one isometry fix these 2 points, then it's going to fix everything along this line. Okay, so now the thing is that if you can accept this is the fact, I'm going to use 15.5 from now on. I'm just going to take it for granted. So not only isometry fix a whole 2 points, it fixed the line, it actually can also transform circle to circle. So the next three theorem, I'm not going to prove it because it's kind of intuitive. So it tells you that if you have a circle and you transform it under isometry, then the image is going to be another circle with the same radius, right? The equal radius. So imagine if you have a circle here, right? And then with some radius r, right? Then if you map it, plugging into your isometry, because it keeps the distance, then it will map to another circle, maybe some with different center. Okay, I don't know. Let's call it O prime. But the image is going to be another circle with the same radius. As you can see that you fix the distance, right? So everything should be within the same distance from O prime, right? So O prime is f of O. This is kind of intuitive, right? Because it's preserved the distance. And same thing happen if you have a triangle, then under the isometry, the image would be a congruent triangle, right? So you have essentially give me some triangle like this, and you map onto the isometry, it becomes another congruent triangle, right? So you know that it's going to be congruent. The reason is you can imagine because it preserves the distance, right? So you essentially have, oops, too much. You have SSS congruent scheme, right? It can be proved because you can say distance between A and B will be the same as distance between A prime, B prime. That's the image, right? And they do the same thing with the other two sides. So right away you have SSS congruent scheme. So you know those two triangle has to be congruent. So essentially isometry also preserves the image of the triangle, right? So the image would be a congruent triangle. And same thing for angle as well. If you map an angle, then the image will also be a congruent angle, right? So for example, if I have some angle here, right, maybe AB here, then after F, the image will be another, maybe different A prime, B prime, but you will have the same angle alpha, right? You can imagine that it opened up the same like width, right, in some sense. So you can actually show that this will be a congruent angle. Okay, so this is not hard to imagine because this is actually very like it's really by the fact that it's a distance preserving, right? So the next two things I want to quick probably I don't have time to prove the next one, but I at least probably have time to prove this one, is that okay? So in neutral geometry, if isometry this time fix three nonlinear points, right? So back then, if it fixed 2 points, it's going to fix everything on the line, okay? But now if you fix three non-collinear points, meaning 3 points which doesn't along the same line, right? Then the isometry turns out to be identity map. What's identity map? Identity map means it fixes everything. So that means if you happen to have this isometry, and that tells you there are 3 points going to be fixed, and those 3 points are non-collinear, then right away it tells you your isometry is going to fix everything on the plane. It's not going to move anything. Okay, so how to start the proof? So you first start with you have an isometry F, and it really fixed 3 points, which means let's say A, B, C are the 3 points it got fixed. Okay, and those 3 points has to be non-collinear, otherwise it wouldn't work. And the first thing is that okay, now we know that there's 3 points. So let's say you have A, B, and C, right? And it got fixed, which means it's the same as its image. Now we can use lemma 15.5, right? If it fixes A and B, then it's going to fix line AB, right? That's 15.5. And at the same time, because it fixed A and C, so it's going to fix anything lies on this line. And same thing, it's going to fix anything lies on line BC, right? So which means if your isometry is not going to move A and B, it's not going to move anything along the line AB. And same thing for the other 3 sides, because mutually you have 2 points got fixed, right? So that means anything on these 3 sides is going to be fixed. So if you plug in anything on that 3 sides, it's going to stay there. It's not going to change. Okay. So that's actually simply just from the lemma 15.5. But the question is, how about any other points outside these 3 sides, right? There's some other points outside, I don't know, right? Is it get fixed as well? We want to prove that if you pick random points not on the 3 sides, it's going to get fixed as well. Okay, that's my goal here. Okay, so now let's see what, so we pick random point, that D be an arbitrary point. Arbitrary point in the plane. And which is outside, which is not on the sides. These 3 lines, right? Okay, because we already know anything along the line AB, AC, and actually maybe I should draw longer, right? Anything on the line AB, AC, and BC is going to be get fixed. So that's good. We already have something get fixed. But I want to prove that outside these 3 lines, any point on outside these 3 lines is also getting fixed. So now I pick some random point D here. Okay, it doesn't matter where I pick the D. I just pick one of them. Then I take E to be a point on the segment AB. Okay, and this point lies on AB and between A and B. Okay, so why I want this? So I want some point here. I don't care where it is, as long as it's not A and B, and it lies in between A and B. Okay, so I said you can pick whatever the point, right? E already got fixed. That's fine. Okay, so now this is exactly where I'm going to use the Pasch theorem. Okay, so first join like line DE. Okay, so let me join line DE. Okay, then what's Pasch theorem says? This is actually one of the axiom, Pasch theorem or axiom from the chapter 6. I can just directly tell you what that is. Then if the line DE intersect the triangle ABC at E, then Pasch theorem tells us that it will intersect any either one of the sides. So it's going to either intersect AC or BC. Right? You can see that depends on where the D you pick, right? Right now you can see that it intersect at BC, right? But if you put D maybe here, right, then it's going to intersect AC, right? So that's why this is one of the Pasch theorem I kind of mentioned earlier, but we didn't emphasize. So this is actually in chapter 6. So you can see, I mean, intuitively, if you connect DE, it's either going to intersect the side BC or AC. Depends on where D is, right? But it's one of them, okay? So without loss of generality, say DE intersect BC at F, right? So let's say it intersect at F, okay? Now let's see, right? So now what do we have? So we know E already got fixed. And also F is also fixed, right? Because F is a point on line BC. We already know anything on those 3 sides is going to get fixed, right? So E is already get fixed. F is already get fixed. So that's what we know, right? E and F are fixed, right? Then by theorem, 15 point, what's that theorem? It's 15.4, fixed 2 point, actually by lemma, sorry. By lemma 15.5. If you fix 2 points EF, it's going to fix all the line in between, right? So it's going to fix, so by lemma 15.5, F, the isometry F is going to fix anything on the line EF. So F is fixed point D, right? Because D is on the line EF. So the logic is once you know DE intersect a point F on the BC, since this isometry is going to fix E and F, then by lemma, we know that it's going to fix anything on this line, which including D, right? And that's it. So we know that we pick some random point D outside these three sides, it's going to get fixed anyway by this argument. So essentially, since D is arbitrarily chosen, so F fix every point D on the plane, right? Which means any point, every point is going to get fixed. So this essentially tells you if you have such an isometry, you know that it's going to fix just 3 non-collinear points, then right away you know it's going to fix everything. It's very strong, right? Because you only need to know 3 points to know the behavior of this isometry. Okay, so sorry, I'm a little bit over time. So I'm going to come back with actually just the corollary, one corollary as an application of 15.9. So what I'm going to ask you, please do me a favor, start preview earlier, because this is going to be very conceptual. If you don't read like in advance, it's going to be very hard for you. Like it's very hard to catch up. So I will recommend that if you have time, please read 15.2 and 15.3. So I'm going to come back to cover this next week. Okay. So if you have any question, feel free to stay.
I had a question about those presentations you mentioned at the beginning.
Yeah. Mm-hmm.
The topics we're going over, like, according to, is there like are you like giving us a list of topics?
Yeah, I'm going to give you a list. Yes, that's for sure. So I'm going to essentially pick out the exercise from the sections that we already learned, like maybe even from earlier, maybe chapter 3 or like 5. I mean, the 3, 2, 6, like whatever the chapter we have covered. I'm going to pick some exercise from the textbook, and then I will give you a list which are the problem I think is suitable, and people can choose out of those lists. So I'm probably going to give like, I don't know, like I'm going to restrict the maximum group to be maybe 12 groups. So I probably will give you like maybe 14 questions to choose from, 14 to 15. And then out of those 14 and 15, some problems are actually for like for one person to present, and some problem because it's much longer, so it's assigned for a group of 2. And but there's only limited group is for individual person, or less like in some limited number of problems are for group of 2. So yeah, so you need to decide that whether you want to do it by yourself or with some other people. Yeah.
And you'll give these topics over the weekend?
Yeah, I'm going to give you like, so you have a list like more than at least 2 weeks to start working on it. And
okay.
Yeah, actually, usually these problems are not that hard, actually, especially like it's from the textbook exercise. And I will take into account that because actually I didn't manage to say that the presentation I'm going to only limit to be like up to 15 minutes. So if you're a group of two, you can only, two people adding together can only be at most 15 minutes. And then for group of one, like a one individual person will only be like 10 minutes if you're doing by yourself. So so it shouldn't be like a very difficult problem because I already tell you that you can finish presenting it in 15 minutes for a one big problem, right? So it shouldn't be too hard. Yeah.
Okay, thank
Okay.
you.
Yeah. So Charles, you're having problem with number 4. So can you remind me what's the number, which section, which problem?
It's finished the last part of the proof of theorem 11.6.
Oh, I see. Yeah. That I remember. Okay, so now let's see. So let me check my picture here. Let me this. Okay, so let's see. Where's my pen? Okay, so I want to know that specifically like what like what's the trouble here? Like, do you know, you don't know how to start, or you don't know why we prove that, or
Well, I guess I'm a little confused on why we're proving that. I can, because you say in the homework, show that AI, BG, and CH are the perpendicular bisectors of the sides. It's easy to show that they're perpendicular, but I guess I'm lost on showing how they bisect.
Okay, so first I want to explain why we want to prove it to be a perpendicular bisector. So so we start with A, B, and C, right? And can you see my screen?
Yes.
Okay, so we start from A, B, and C. The whole point of this theorem is to prove that if you have 3 altitude, right? You can draw 3 altitude. You want to show that it's going to intersect at a single point. That's the concurrent, right?
Right.
But we don't know yet. We want to prove it. But we don't directly prove it. The way we do it, or the way this textbook did it, is that, okay, those 3 are the altitude. But what if I can turn this altitude into the perpendicular bisector of some other triangle?
Okay.
That would be great, right? Because we already proved in, I think, theorem 11.3 or 4, I forgot which one.
1.3, yeah.
Right, 1.3, which says that 3 perpendicular bisector is going to intersect at circumcenter, right? So now that's exactly what we want. But then we want to show that this 3 altitude is going to become the perpendicular bisector for a bigger triangle. And then to prove the perpendicular bisector depends on how we construct the triangle DEF, right? So I didn't actually include the construction part in the homework. You need to actually go to see the textbook, like they have detailed like construction. Actually, I kind of mentioned it in my lecture note as well when I taught this, I think on Monday or last week. Last week, yeah. So the construction is the following. How do you come out with DEF, those 3 points? You first construct a line passing through L, and you call it passing through A, sorry, and you call it line L. And you want this line L to be parallel to BC.
Right.
Right, and that's the first line. And you say, okay, I'm going to construct another line passing B, parallel to AC, and that's called the M. Parallel to AC, right? And you do another line passing C, and that's called the line N, and then it's going to parallel to AB, okay? And you code this line N. And last time I actually did briefly go over, like explain that you can prove it. I'm not going to ask you to prove it in this homework, but you can prove it. These 3 lines will mutually intersect each other at D, F, and E. That's how we construct the larger triangle DEF.
Okay.
Okay. So now the point is that, okay, I'm claiming that I mean, actually my picture is a little bit bad because I can see it's not very accurate. But anyway, so now I want to show that the altitude is going to become the perpendicular bisector of the bigger triangle, right? So let's say, let me see, how did I code the points here? That's called this I think that's how they code it. And I code this J. Okay. So now, if you know how to prove one of the altitude is a perpendicular bisector, then you should be able to prove the other two because the proof will be very similar. Okay.
Right.
So I'm going to tell you how to do one of them. Okay.
Okay.
So the one of the goal is, okay, you want to prove this line AI, which is the altitude, right?
Mm-hmm.
It's going to be perpendicular bisector for DF. Perpendicular bisector of DF, right? Which means you need to prove two things. AI is perpendicular to DF.
Which that part's easy.
Yeah, that part is easy. And then actually the other part is not bad. The bisect part, if you found the picture, you actually want to prove AD is equal to AF, right? That's the bisect.
Okay.
I mean, my picture is a little bit bad, so that's why it doesn't, yeah. Okay, this part is, okay, first part, I want to make sure you know you get the first part correct. So you can see that it's already perpendicular to BC, right? The altitude, that's because it's altitude. But you know BC is parallel to this DF, right, by the construction.
Right.
So then this angle, or I mean, it depends on which angle, right? If you look at the alternate angle, it should be the same, right? Because you have two parallel lines, and you already know this angle is perpendicular because it's the altitude. So the alternate angle here should also, so DAI is also 90 degree. Is that how you prove it?
Yeah, I was thinking like Euclid's fifth postulate. I was thinking like FAI.
Because that's also the same, right? FAI add up to RNAD. Yeah, that's the same thing. Yeah, so that's fine too. Yeah, so you can prove that's 90 degree. Now the bisect is actually not too bad because now it's also going to use the fact that you have so many parallel lines, right? So now if you look at A, B, C, F, do you agree that it's a parallelogram?
Yes.
Right, because there's so many parallel lines. Okay, if it's parallelogram, then right away by proposition 1.34, AF is going to be the same as BC.
And then you have the
D, yeah, exactly.
Okay.
Yeah. Then you do that.
There.
Yeah.
All
so
right,
now do the same thing for the other two, right?
Okay.
Okay.
That makes so much more sense. All right, thank you.
Yeah, you'll come. Okay. Good luck.